So let us go on to the next subtopic of this chapter, that is on exact equations. Okay. So before going there, we'll have to do a little revision of derivatives and partial derivatives. Okay. So let us just do this revision first. Okay. So what we're studying right now is called exact differential equations. Okay. Just a little bit of revision first. So first thing what we'll revise is partial derivatives. Okay. So what are partial derivatives actually? Let f be a function from r2 to r. Okay. So f will be a function of how many variables? Two variables. It will be f of x, y. Okay. So f of x, y is going to be something like this. It will be some combination of x and y. Okay. So now, unlike what you had studied till now, you had studied functions of this is function in x and y. Variables x and y. Function in variables x and y. Okay, so the derivatives which I have studied till now, they were only functions of one variable, that was x, and you all took derivative with respect to x. But now you have two functions over here, right? Two variables over here. So there is one more new derivative which comes up, that is called a partial derivative. Okay. So what is partial derivative basically is the exact definition is going to be this. We denoted by partial derivative with respect to x, partial derivative with respect to x okay. This will be denoted by dou f by dou x, not your regular d, this is a dou. Okay, so you will be using d, right, for regular derivative which I studied. This we are using a Greek alphabet, that's called dou. Okay, it's pronounced in the dou, d-o-w. Okay, it's written with a little curve, it looks like d but it's not d. Okay, so this is defined as limit of h tending to 0 f of x plus h comma y minus f of x y divided by h. Okay, so what I have done here, this is same like your original derivative which I have studied, but look something carefully here. I have brought about a change only in x. Okay, so there is only a change in x divided by the change in the variable, that is h. Okay, so change in x is, there is only a change in x, that is x plus h. X has shifted to x plus h and the function has changed accordingly. There is no change in y, so y is kept as constant. Okay, and then we are taking the derivative. This is your usual definition of a derivative, right, what I have studied. So this is how we define this. Same way we define also the partial derivative if the limit exists. It might happen that this limit is not existing also. So then we say that the function is not partially differentiable. The partial derivative does not exist. Okay, same way we can have a partial derivative with respect to y. So that will be denoting by dou f by dou y limit of h tending to 0 f of x plus h comma y minus This will be, I'll use the different alphabet, J, K, H, L. Yeah, K I'll use, H, K. So x, y plus k, okay, f of x comma y. So this is the same definition as derivative, but I've kept x variable as constant and shifted only my y variable and divided by the change. Okay. Yeah, you can think of the denominator like this, by the way. So this change in the y coordinate, that is only h, only k. Same, this was x plus h minus x over here. I just written it as h. Okay, so if you wish to write it like that, you can write it. Okay, so change in x, change in the domain, and change in the codomain divided by change in the domain. Okay, so this is their partial derivative with respect to y if the limit exists. It might happen the limit does not exist. It can happen that only the partial derivative with respect to x exists but not with respect to y. Okay, that can also happen. Sometimes you'll have only partial derivative of x but not y. Sometimes you'll have y but not x. In same way, some other possibilities also are there. Okay, so this is there. So another thing next is we'll see some examples on this. First one, f of xy. F of xy, we'll take it as x square y plus sine of y into cos of x. Okay, so we'll take this as a function. So now dou f and dou x, the partial derivative of this with respect to x. What's going to be? I'm going to take each of these terms. I'm going to treat y as a constant. Okay, the y term will be treated as a constant term. So this will be a 2x y as it is, and then sine y is a constant. So cos x derivative will become minus sine x. So minus sine x sine y. Okay, minus sign came from this. Same way now, what will be the partial derivative of f with respect to y? This is going to become y. I'm going to take derivative. I'm going to keep x as a constant. So x square will remain as it is. Derivative of y will become 1. Okay. Next, I'm taking derivative of y over here and keeping x as it is. So sin y will become cos y into cos x. Okay. Same way, I can continue this way. I can continue this way. I can just how you define a second derivative, we can define a second order partial derivative here. So this will be what? This will be taking derivative of this another time with respect to x. So 2xy. So this will going to be remain here as 2y sin x sin y. So derivative of sin x is how much? So this is going to become cos x. Okay, cos x sin y. Okay. Same way, do the same thing with the other fellow. Derivative of this with respect to y. Is there any y term here? No, x square is a constant, so derivative will become 0. And here there is a y term and there is a x term. So x term will treat as a constant, take derivative only of the y term. So this is going to give me sin y into cos x. Okay, so this is what I have over here. Also, you can define things like this. This is basically wait a minute, let me just emphasize on this. This quantity what I have written here is basically dou by dou x of dou by dou f by dou x. Okay, this is how we define a second order derivative. In the same way, this is dou by dou y of dou f by dou y. Now we can also define this quantities like this. We can also define, you can write on the below line, dou f by, and define dou by dou y of dou f by dou x. Okay, so this is called as mixed partials. Okay, because we are taking one x, one y. So dou f by dou by dou y and dou f by dou x. Okay, so I am mixing both of them. So this is same as writing dou f square by dou y dou x. Okay, in short notation, this is how we write it. Now how we'll take this derivative? I have already found out dou f by dou x, right? I take its derivative with respect to y now. Okay, so take this one's derivative, this quantity's derivative here with respect to y. So x you're going to treat as a constant, y is only 1, so derivative of y will become 1. So this is going to become as 2x. Here you have sin x will be a constant, sin y will is a variable now because we are taking with respect to y. So this derivative will turn out to be cos of y. So minus will remain here, sin x cos y. Okay, clear to everyone how I got this? Okay, same way, let's do the other one. Dou by dou x, dou f by dou y. Okay, so this gives you dou f square by dou x dou y. Okay, this is a shorthand notation for writing it. So take the derivative of dou y and take derivative with respect to x over here now. Okay, so x square derivative will become 2x. Okay, here you are taking derivative with respect to x now. So cos y is a constant, cos x is a variable function. So I'll take this one's derivative, will become minus sin x. Okay, so which gives me the same thing. Okay, observe that observe that these two quantities are equal. So it didn't matter whether I took the derivative of x first or derivative of y first, the quantity came the same. So let me try one more function now. Practice will do one more. Second example. F of xy equal to x square y square, okay, plus e raised to xy plus sine of x square y. Okay, so let us talk about this one now. So we have dou f by dou x coming first. Okay, let's do this. X square will take derivative, y square will keep as it is. So 2x y square, okay, 2x y square, and here we'll be having e of xy. Exy, yeah, derivative of this with respect to x, what will it be? Derivative of e raised to x anyways remains the same thing, right? But there's a constant y over here, so what we'll have to do? Okay, by chain rule this quantity will have to come down here. Okay, so it's derivative of e raised to x multiplied by e raised to something. This is, so derivative of e raised to something is the same thing, right, multiplied by derivative of the something. So derivative of x into y will turn out to be only y. Okay, yeah, moving on now. What will this derivative be? This is sine of something, right? So it's going to become cos of something, multiplied by derivative of this something which you have inside, and that will become 2x y. Okay, next, dou f by dou y. Do the same thing. It appears to be very much similar. So this will become 2y x square plus x e raised to xy. Okay, because the first two terms are symmetric with respect to x and y. Whatever happens to x will also happen to y because they are symmetric. Okay, so x square y is same as y square x also. Y square x square. Okay, this term will become different now. This will become cos of x square y multiplied by derivative of the inside term with respect to y. So y will become 1 and x square will remain here outside. So let's go further. I'll find the derivative of f with respect to x again. Okay, second order derivative here. This will become 2x will become 2y square. This will become, repeating the same process here, y is a constant and derivative of e raised to xy you have to take. So that y will come down one more time. So it will become y square e raised to xy. And this will also have the same consequence here. But now notice that there are two terms. One, this is a function of x, cos of something multiplied by this thing. So now you'll have to use product rule over here. Okay, so this will become, first term will become minus sine of x square y multiplied by, again it will 2xy will come out common, right? So I'll write 2xy the whole square. Okay, and plus take derivative of the second term. So that will become cos of x square y into cos of x square y into this will be multiplied wait, this won't come now like this. Sorry, this will not be like this. This I'm taking derivative with respect to y over here. So this will become minus sine x square y, okay, into derivative of the inside term. Inside term will be, derivative of inside term will be only x square because I'm taking derivative with respect to y. Okay, and then I multiply this with oh sorry, I was doing this one. I thought I started the y case. 2xy. Okay, I was right. Okay, I was right. Then they have to just take the derivative of this thing. Cos of x square y. This derivative will become only 2y. Okay, so this is all we get. We can go further to the third derivative and all. This will be difficult for this problem. Not impossible, but you'll have to sit and just calculate terms here. Okay. Same thing we are doing with respect to y. Dou square f by dou y square. The first term is 2y, so that will just become 2x square Repeating this, we'll get another x square. This is not a product of two functions because there is no y term involved in the second part, right? So it's only one term of y. So it's going to become derivative of cos, that's going to give you minus sine of x square y into x square the whole square, that's x raised to 4. Okay, now moving on, next let's talk of the mixed partials, that is dou f. We'll do the other case first because I have to scroll on top of it. That's why. Okay, taking partial derivative of the x term with respect to y. So this is going to be 2xy square. So take derivative of y over here. This is going to give you 4xy. Okay, so 2x into 2y is going to give you 4xy. Derivative of this with respect to y. Now there are two terms involved. So first I'll take the derivative of only the y term, that is this, plus keep the y term as it is and take the derivative of the remaining terms with respect to x. Sorry, with respect to y. So it's going to be derivative of e raised to xy with respect to y. So this is going to give you derivative of e raised to xy multiplied by derivative of this top quantity. That's only x is going to come out there. Okay, but since x is a constant, x comes down. E raised to xy. Next, derivative of the remaining terms. Again, there are a y here. So it's going to be a product of two. Product rule will have to be applied. So derivative of cos is going to give you I'll write it like this, minus sine x square y x square y 2x. With what I'm taking, this I'm taking with respect to y. So only x square will come out. Okay. Plus, not plus, this is going to be xy as it is. Plus derivative of the second term, that will be cos of x square y into 2x. Okay, because that y is going to go from there. Okay, so these are all the terms involved here. Now do the same thing of taking derivative of the other term with respect to y. So dou square f dou x by dou y. So this dou y term, the second dou f by dou y, I am taking derivative with respect to x. So that's going to give me again 4xy over here. Again I'll have to use product rule over here from the second term. Derivative with respect to x is going to leave you with only e raised to xy here. Then when you take the derivative of the second term, y is a constant, right? So derivative of e raised to xy will be e raised to x multiplied by e raised to xy multiplied by y. Okay, the constant comes down. So this is going to become yx e raised to xy. Okay, so far we are same. Next we have cos of x square y. Okay, yeah, there's only there are two x terms anyways here also. So this is going to become minus sine of x square y derivative with respect to x taking, no? So it's going to become a 2x over inside. Derivative of the inside term, no? So 2xy it will be. Okay, so multiplied by 2x y, and there was an x square already over here. Okay, x square was already there, plus derivative of this second term with respect to x. So that is going to leave the first term as it is. cos of x square y into 2x. Okay, so one thing you can clearly see here, okay, so this is the conclusion we get for this function also. So basically there is a theorem which tells us when this will happen. It is not always true, but unfortunately I can't give you the examples where this fails. Okay, the examples where this fails requires a little bit of more theory to calculate. Okay, so we are not doing this theory right now, we will study it in semester 5 or somewhere, or 4 or 5 something, this multivariable calculus. Okay, so by and large all the functions which are dealing with this will happen. Okay, okay, so let me just state the result. I'll go ahead. Okay, so theorem, this is called as Young's theorem. It's called as Young's theorem. It's named after a physics guy who also has other results named after him. It's the Young's number or Young's ratio something. Okay, so Young's theorem. So what does Young's theorem tell you? Let D be a subset of R. 2, F be a function from D to R. Okay, let x naught y naught be a point in D such that both such that both both dou by dou exist and are differentiable in some neighborhood. X naught y naught. In some neighborhood of x naught y naught, then okay, then this result will be true. So basically this is a very simple condition for a function to satisfy, at least the ones which we are dealing with. Okay, the partial derivative should exist and will be differentiable. So almost all the problems which are solving, their partial derivatives exist and they are differentiable. Okay, so that's not a problem. The ones which does not exist or where they are not differentiable are very bad examples which I can't teach all right now. There's some theory involved in that. Okay, so whatever examples we are doing, so this result will be true. That's what I'm saying. Okay, so don't have to worry. There are some examples where it does not work. Okay, where this equality does not hold. The order matters. Which one you're taking first. Okay, so moving on. The next thing what we have to know is Okay, so next thing what we have to know is called as the total derivative. Okay, so let f from R2 to let R2 to R be differentiable at a point x naught y naught, then the total derivative of f is given by df is equal to dou f, okay, dx plus okay, so this is the value of the total derivative. This is how the total derivative looks like. Okay, so df is written equal to dou f by dou x multiplied by dx, okay, then added with dou f by dou y multiplied by the total derivative of f is dou f df is given as dou f by dou x multiplied by derivative with respect to x multiplied by dx actually, and dou f by dou y multiplied by dy. Okay, you all can think of this is not a correct assumption here, but you all can think of it like this, that you are applying chain rule over here, right? So what happens when you are applying chain rule? You will first take the derivative of the function with respect to the inside variable, right? Okay, so that's what I'm doing here. So my f is a function of two variables, f of x, y. So first I took the derivative with respect to x and multiplied it with rate of change with respect to, sorry, change of x, not rate of change, this is just change of x dx. Okay, then other option is dou f by dou y, it's the change in y multiplied by dy. Okay, so basically what I'm telling you is, if you change your x, if there is a change in your two variable function, that change can be in x or change can be in y. Okay, so since there is an or involved here, I'm using a plus sign over here. If there is an and involved, we use a multiplication sign. Okay, so that's this thing. Let me just go further. So this is, you can think of this as a notation to just write down things. There's some theoretical meaning of this expression which I've written, but we won't be studying that in this course at least. So in that, I don't need to get into all the details of this. Okay. So now, moving on. So this is the end of the revision part. I will start with our actual exact differential equation. So many differential equations can be expressed as right. We have seen this now before. We've seen that differential equations can be written in this form. We have written also a couple of differential equations like this. Okay, a function of m is a function of x and y, and n is a function of x and y. Okay, we wish to find now what is our intention over here is, if this is a differential equation, we'll try to compare it with the total derivative over here. So can you see that this mxy is stands in the same place where dou f by dou x is standing, right? It stands as the coefficient of dx. Same way, n of xy stands here instead of as a coefficient of dy, and here the coefficient of dy we had said is dou f by dou y. Okay, another thing we had said the total derivative of f is df, but that quantity here has gone down to 0. Okay, so the question is, can we find a function, continuous function more importantly, sorry, not a continuous, we require a differentiable for this, huh? Can we find a differentiable? Because if it is not differentiable, there is no point in talking of all derivatives here. Can we find a differentiable function? Differentiable can we find a differentiable function Can we find a differentiable function f of xy such that the derivative of this comes at this position? Okay, so that this two are same. Okay, so I can say that such that 1 and 2 can be made same. Okay, so basically what I'm asking you, that is, if this happens, that means dou f by dou x should be made equal to m. Okay, and dou f by dou y should be made equal to n xy. I won't write this xy later on, I'll just call it capital M, capital N now. Okay, and also what is the other condition? This has to be equal to 0, right? So we are saying dou f is equal to 0. Now if your total derivative is equal to 0, okay, this means that the function 3 equal to means the function is defined like to be 0. Okay, always 0 kind of. Okay, now if this is equal to 0, this implies that total derivative is 0, so this also has to be 0, and dou f by dou k, dou f by dou y has to be equal to 0. So if the, now you know this things, if the derivative of a function is 0, what does it mean when you study in 12th standard? What kind of functions have 0 derivative? Constants, right? So here I'm talking of a function which is supposed to have f is a function of x and y, right? Okay, so thus this function f of xy, it should have been a function of x and y, but when you take its derivative with respect to x, you're getting a 0. So what it means, there is no x term in it, it's just a constant with respect to x. Now if you take its derivative with respect to y, again you're getting a 0. So it means that there is no y term also in it. See, if there is no x term in the function, it's basically a constant function, derivative becomes 0. So now since we have two options here of x and y, okay, what I'm saying is, if the derivative with respect to x becomes 0, that means it's does not have x term in it. If derivative with respect to y becomes 0, that means it does not have y term in it. Okay, so both the derivatives dou f by dou x and dou f by dou y are both 0. So there is no x term and there is no y term. So who should be there? Only a constant, right? So this is a constant. Okay, so now, so equation of a function equal to a constant, this describes this quantity describes a family of curves What do I mean by family of curves? For each value of c, for that is for each value of c, we get a new curve okay, we get a new curve, but these curves have one property. What is that property? That they are kind of parallel to each other. So if you take equation of lines like y is equal to mx plus c, and you keep on changing the value of c, what you'll end up in getting is lines with the same slopes, right? Because you're not changing the value of m. But what will happen is, since the c value is changing, we'll get a new line which will be parallel to your previous line. Okay, so same thing is happening here also. You're keeping f of xy as a constant, so you'll get some surface. Okay, that some surface will be there like this. So that surface, above that surface you'll get one more surface for a different value of c. So another value of c, you'll get another surface, and none of these two surfaces will be intersecting with each other. Okay, yeah. So just 1 minute more, we'll write this down. So now how to find this family of curves is the question. So we'll start with what we had done above. Okay, to find, this is method to find this thing. Method to find f of xy. So what have we seen? We have dou f by dou x as m, right? And dou f by dou y is equal to n. Okay. So then dou square f by dou x, dou y, dou x. I'll take the derivative of this with respect to y. So dou m by dou y, and this I'll take it with respect to x. So dou square f by dou x dou y is equal to dou n by dou x. Okay. Okay, so we will just, since the functions are nice, have nice. Okay, nice means they satisfy the condition of the theorem above. Okay, so we have nice smooth functions. Smooth means basically they are differentiable. So I'm not getting into the details of this condition. Smooth functions, continuously differentiable functions are called smooth. Okay. what will happen is dou f, then this dou f square f by dou y dou x should be equal to dou square f by dou x dou y. Okay, so this implies that dou m by dou y is equal to dou n by dou x. Okay, so this is called as the hence a summary of what I have done. By the way, what I have done here is notice here, just I assume that dou f by dou x is equal to m, and I had assumed that dou f by dou y is equal to n. So if these two conditions are true, then this condition holds true. So this is basically if P then Q. Okay, you will have studied logic now in other paper by now. So now if this statement is false, if Q is false, will P be true? No. Okay, so now hence we get to conclude that, so this means basically that the solution exists. Okay, so this you can write there a different color. Solution exists, solution f of xy exists. If the solution f of y exists, then you can write this, right? So if the solution exists, then this condition should be true. Okay, but if this condition is false, then solution will not be existing, or solution can't be found. Okay, so the conclusion is hence we need dou m by dou y is equal to dou n by dou x is a necessary condition for us to find the solution f of xy. Okay, see, for you to say that this happens, now you should be able to find a solution. Okay, f should be able to found out. So if that solution can be found, then this happens, right? So if this does not happen, then this will not happen, you cannot find the solution. Okay, so that's what I'm saying. So that's why dou m by dou y is dou m by dou y equal to dou n by dou x is a necessary condition. If it does not happen, then you cannot easily find a solution. Okay, there are some other techniques, but still, okay, we'll learn them later. Okay, so this is a necessary condition to find a solution f of xy. This is called as the exactness condition. Okay, so exactness condition. Okay, so we'll stop with this, continue in the next class.